So thank you. I'm going to be talking about SPEW, which stands for Synthetic Populations and Ecosystems of the World, and it is an R package to make practical synthetic ecosystems. This is joint work with my fellow student, Lee Richardson, and professors Sam Ventura and Bill Eddy at Carnegie Mellon University Department of Statistics. The prevailing philosophy for our synthetic ecosystems and why we make them is that better synthetic ecosystems means that we can have better agent-based models. So this is not only our prevailing philosophy, but also our goal. We want to make these synthetic ecosystems that are in a standard format, a data structure, as you said, that can be useful for others to use in agent-based models and other complex systems. So I'm going to be talking about how we go about making these, what we call better synthetic ecosystems. So agent-based models, as we all know now, simulate phenomena, and there are many different examples in ecology, epidemiology, sociology, and more. I'm mostly looking at this from an epidemiology standpoint. We're under the MIDAS grant, which stands for Models of Infectious Disease Agent Study. And a couple agent-based models in that field are, one is FRED, which comes from the University of Pittsburgh, and another is EpiSIMS, whose creators are sitting next to me today. And so agent-based models are useful in that they allow input from experts. Not so much mathematical knowledge is required, and they also take advantage of the low cost in modern computing, which we heard about earlier today. And as was mentioned, simulation of events can happen in multiple ways that science normally can't occur. So either an experiment may be impractical or even was, as mentioned, unethical. And I was thinking of coverage for vaccination, how many people we need to vaccinate, but I suppose more nefarious methods could be used as well, but we hope not. So agent-based models, as the name perhaps implies, require these agents to be useful. And we define agents as a set of objects with varying characteristics. And so that's sort of vague, but we can think of agents rather concretely. We can think of them as mosquitoes, for instance, or we can think of them as people. And I will refer to them in this talk as synthetic individuals, synthetic mosquitoes, or what have you. And then also a very important part of these agent-based models is the environment. And this is where the agents interact. And it's a constrained location and where agents update one another and evolve their activities. The synthetic we have here means that they are simply created from data via statistics. So this is where this data integration comes into play. And we have a bit different terminology. What we call the agents in the environment together, we call an ecosystem. And so when we create it from the data, it's a synthetic ecosystem. So SPEW, as I mentioned, is an R package that generates these synthetic ecosystems. And it stands for, as I said, Synthetic Populations and Ecosystems of the World. And what it is an interface for the modeler to be able to create synthetic ecosystems in a standardized format using your data or whatever data is available. And we also have a number of pre-made synthetic ecosystems online. And using R, if you're not familiar with it, it is a language, a programming language, and as it's coming from a statistical point of view, we really enjoy it. It is very well documented. It is popular. It has interfaces with C++ and all sorts of languages. It works well with data manipulation and especially spatial data as well. So if you've never given R a shot, we recommend it. And so what we do is what we're mainly looking at today is this framework of how we generate synthetic ecosystems. On the top level here, you can see we mostly have our input data. Those are all input data. And I'll define what those mean in just a second. And what's important is that this input data needs to be harmonized together. This data needs to fit together so we can use sources simultaneously. Now, I'm not going to be talking too much about the top half of this diagram today, but I am giving a tutorial workshop on building a synthetic ecosystem of LUCA on Friday morning, which I will talk in depth about data collection and harmonization. But I'm going to talk more about the core of SPEW, which is the synthesis process, as well as the outputs it provides, which are downloads of our synthetic ecosystem, so it can be hooked up into your agent-based model, along with visualization, so we can look at a synthetic ecosystem as a whole, and validations to make sure that we know our populations are accurate, and what accurate means does differ. So SPEW works at the subregion level, and I just wanted to define what we mean by subregion. So I partitioned Italy into different administrative regions. It's kind of hard to see here, but what we have is different administrative levels. In each of those partitions, any one of those pieces we would call a subregion. The important part is that they're discrete pieces that do not overlap. But SPEW can work on any one of those regions, big or small. So once SPEW has the data and it's been harmonized, the process is fairly straightforward. And what happens is that we sample population characteristics of agents, and then we assign locations to those agents within the environment, and finally we assign the agents to environmental activities. So to motivate why we need methods of sampling characteristics, we all know that people have different characteristics such as race, age, income, and more. And moreover, we often know that these characteristics are related jointly, so they may be dependent upon one another, for instance, age and income. And so what we do is we need to assign characteristics to agents that is realistic in a statistical manner and makes sense. So we have to be clever about how we do our sampling. And right now, our program supports 3 different methods, iterative proportional fitting being one of those, which was talked about earlier today, and another couple methods as well. And I don't have time to talk really in depth about all 3 methods, but as you can see here, there are different advantages and disadvantages to each. And iterative proportional fitting, we see, has many advantages, but you can also see in the data required, it requires the most. So although we prefer it in most situations, sometimes the data is not available. So SPEW takes the philosophy that we do what we can, and if we have the data, we want to do more sophisticated sampling methodology, but otherwise we can make do with the data we do indeed have. Once we sample the population characteristics, we need to sample agent locations. And so here is a map of LUCA, and we have 2 different sampling methods demonstrated here. So I drew a box around LUCA, and I simulated, I think it's 1,000 agents, which are the green dots inside each of these boxes. On the left-hand side, we have uniform sampling. And while it may appear not to be that realistic, and in this case, it doesn't seem to be, if our region boundaries are small enough, and sometimes they do get rather small, for instance, census block groups are very, very small geographic regions, then if we're sampling uniformly within those regions, we are at least maintaining population density. So I think uniform sampling does better than it initially looks. However, if we do know information about the spatial distribution of agents, then we do prefer sampling from it. And on the right, we have something we called road-based sampling, where we extracted the roads in this LUCA region and sampled agents along the roads, the idea that people seem to live close to roads. So if we do have information such as roads or even housing information, we would like to use that. But again, some of that data can be costly and difficult to obtain, so we make do with what we have. We also use a gravity model to assign agents to shops, or excuse me, just environment locations in general. And here's an example of our agents in Luca. So here's a teaser for Friday of what we're going to generate during the presentation. And I have agents within Luca who are the dots, and they have different colors, so they have different shop assignments. And I just chose these 6 shops randomly, pretty much for illustrative purposes here. And we can see that the agents are assigned based on distance, and you can sort of tell that with, say, the orange triangle up there, which is one of the shops. Many of the agents who are up there are orange, but in the bottom half of the figure, there are very few orange agents. So it seems that people go to shops that they are closer to. And the idea with this gravity model is that it's based on both distance, but it's only shown distance here, but also capacity. And it is a flexible function where the user can input exactly which distance function or capacity based on some constraints within SPEW. So here's an example of what our outputs look like in SPEW. And so it's a tabular format that we hope is useful for the modeler. And each row has an agent, and each row corresponds to an agent and a different individual. So this lady right here, she's my favorite, agent 1038094, and she has a household income of $34,000. And you can see here she attends or she works. And we can just see that these are very different agents. Here's this person right here who happens to be 11 years old and attends school. So we have very different agents within our outputted tables. And along with that, each table contains a regional geographic identifier, so you can find the synthetic ecosystem that you are trying to use, for instance, Luca. And the environments, which here would be the schools and the workplaces, they can be either recovered straight from these tables, but we can output them we also output them as separate tables. So there's a lot you can gather just from looking at these synthetic ecosystem tables. Another important feature of SPEW is that it is parallelizable, and that just means, as many of you know, we can run many of these at once. In SPEW, it works in a basic level, so this is built into SPEW's functions, so it can run on anything from your laptop, which I've done before, to a supercomputer to make millions or billions of agents all in just a few minutes. So using parallelization, we can greatly speed up the process of our synthetic ecosystem. And for an interested modeler, like doing counties at a time on your laptop, it would take probably about 30 seconds or so. So not long at all. So I've mentioned this a little, but I want to go into a little bit more depth in that the synthetic ecosystems require different data. And the ones that we have available right now do use different data. We're from the United States, so we're most familiar with US data and obtaining it. So with that, we've been able to synthesize more sophisticated synthetic ecosystems using iterative proportional fitting and row-based modeling. The United States regions here are in blue on this figure, where the x-axis is the log total number of people or agents, and the y-axis is the log seconds. So we can see it seems to be a linear relationship within the groups, which are different colors. The green dots are what we call IPOMS regions, and this is what a set of harmonized data that comprises different countries throughout the world, at about 75 or so, and it's harmonized, so it's its own set of data. And then Canada's kind of doing its own thing there as well. We have our own set of data for that. And we're running this on Olympus, which has 24 nodes total and 64 cores per node, which is only a few 100,000 less than what I think HLRS can do. And what we've been doing is that we can run all these in about 83 minutes. So along with our synthetic ecosystems that we have generated, we also produce summary reports, because we all want to know what our synthetic ecosystems look like and if they are correct. So here's a snapshot of our synthetic ecosystem report for Italy. And as you can see, there are about 59,800,000 people, and these are typically available online. And here's just some of the figures that this snapshot contains. We can see a population density map of the regions of Italy, along with the number of households for the different regions. And there are other important factors as well, along with information about how the synthetic ecosystem was generated. And so you can download all the synthetic ecosystems for the countries colored in blue. The red ones, we're missing one essential form of data, so we're pretty close to making those. And then the black ones, we're a long way from getting good enough data to make a synthetic ecosystem. So as you can see from this map here, we're slowly conquering the world. And what we're working on right now is we're incorporating disease vectors, so ticks, mosquitoes, that sort of thing, how these will fit into our synthetic ecosystems. And in the figure there, you can, that is supposed to be the population density of mosquitoes in the Italy. And this was with a program called MaxEnt. And we're also looking for direct synchronization with agent-based models. We really are hoping to hear from the modelers what they need to use these synthetic ecosystems, and in general, how they can be more useful. We're looking into the inclusion of more data-driven interactions, the activities of our agents, and we're always looking for more and better data. As you can see here, our map of Europe is a little sparse, so even if we could do a better version of Europe, that would be a good start. And so just as a takeaway today, with SPEW, if you have an agent-based modeler that has harmonized data, or just data, you can choose the sampling method of individual characteristics, assign the locations in a way that makes sense, and also environments. And this will create a synthetic ecosystem within SPEW. So this is all what SPEW does, what you can do if you have the data with this R package. And you can also visualize and validate the output. Conversely, we also have many pre-made synthetic ecosystems online. We have 75 different countries, and those are available for use. So we're happy to help build synthetic ecosystems, and if you're interested in making them, please feel free to contact us. I just want to thank everyone here for the Midas people and the Pittsburgh Supercomputing Center, where we made our synthetic ecosystems, and it's a real pleasure to be here today, so thank you for that invite.